Hi. Today we're actually going to wrap things up with electron structure, finally, and talk about how electrons filling in doesn't always line up with what we'd expect, even though we've talked about already subverting expectations. So as I do now, hit the pause button if you want to do this one on your own. We'll link to the reference table above our heads, my head. I want you to give the three different electron configurations that we've learned about for a sulfur atom. I'm going to get started. The number underneath sulfur is atomic number 16. Underneath we have 286. So this is going to be the Bohr notation. To turn that into a subshell notation, we just split this up into our principal energy levels and our sublevels from there. So 1s2, 2s2, 2p6, and then the final 6 electrons go into 3s2 and then 3p4. And then for the orbital notation, we're probably going to need a lot more space, but each of these sublevels is now going to be broken up into their composite orbitals. That's 1s, 2s, 2p, 3s, 3p. 2 there, 1, 1, 2. And then for 3p4, we've got 1, 2, 3, 4, so that we end up with 2 unpaired electrons. And this is where the orbital notation really has its power. I didn't mention this before. You can see whether or not there are unpaired electrons in your atom, and that's more useful than things you'd see elsewhere with the other configurations. For today, I don't know if you've noticed this yet. Some of you may have, but it turns out that the numbers we see on the periodic table don't match. We said that the cap was 2n squared for the maximum number of electrons. So if n was 1, you can fit 2 electrons. If you're for the second energy level, 8, and for the third, you could fit 18. So you figure we're counting in order, we're adding 1 electron with each of these subsequent atoms. Sulfur has 16, chlorine 17, argon 18, potassium 19, 286, 287, 288, 289. Not 289. So why is that happening? Okay, that's what we're doing today. The best way I can make sense of this is I actually want to go through and do the subshell notation for each of these. Now, in order to save ourselves a little bit of time so that I don't have to be drawing for the next 12 minutes, I'm just going to show the outermost 1 to 2 energy levels. As you can see, the 2-8 is in common for all of these. So we're really just going to start with the third energy level. This will be 3s2, 3p4, 3s2, 3p5, 3s2, 3p6. And then when we get to this next one, we've got an 8 and a 1. Well, that 1 means it's in the fourth energy level. So we have to conclude that this is 3s2, 3p6, 4s1, 3s2, 3p6, 4s2, 3s2, 3p6, 3d1, 4s2. So it actually seems to be, if we were counting in order using these subsequent atoms, we can kind of figure out the order that the electrons fill in, that it seems to be that 3p6 fills up, and then the next electron actually fills into 4s. And then once 4s is full, we kind of double back to get 3d. And the idea behind this is that while we're kind of looking at it as the individual electrons filling in, the safer way to think about it is to say these electrons as a whole are organizing themselves into the lowest energy configuration. So our conclusion is when you have 19 electrons, they fill into 1s, 2s, 2p, 3s, 3p, and 4s. Not 3D. In a way, you can kind of say that, that means that the order of orbitals isn't what you think it is. But all I'm saying is the Aufbau principle is that lowest energy gets filled first. That is to say the group of lowest energy orbitals, because sometimes we're going to see that what we expect isn't what actually happens, and it's even more complex than this, but I'll save that for a little later. A lot of people consider the Aufbau principle to say, hey, it goes in the wrong order. No, it goes in the right order. We just don't know what the right order is yet. But we can figure it out by taking a look at these elements. So I took a snippet out of the fourth row, period 4, of the periodic table, and we can play this game again, and we can figure out what's being filled. So here we have 3s and 3p, and that fills up through here. So the subshell that we're filling here is 3p. The subshell that we're filling here is 4s. And then the subshell that we fill between scandium and zinc is 3d. And then gallium, it says 2818-3. So from here on out, we're still filling 4p again. So it goes 3p, 4s, 3d, 4p. And if you go through this process of looking at each subsequent atom, you can figure out which orbital would be next. That said, I did that for you to make your life a little easier. And this is the picture I like seeing. Order of orbitals, of subshells actually, sublevels. The reason why it works like this is that we had said before on your energy graph that 1s is way down low and that 2s exists, but then 2p is slightly above it, and then 3s is above that, and then 3p is above that. But remember that we've seen in previous lessons that subsequent energy levels are closer in energy than the ones before. 1 and 2 are farther apart than 2 and 3 are, and 2 and 3 are farther apart than 3 and 4 are. So actually, one thing that ends up happening is because they're getting closer and you're adding more energy levels, it just flips over at the 4s energy level that 3d is a slightly higher energy than 4s. And then you continue with 4p, but then it actually works out that 5s fits in there before you get back to 4d and then 5p, and then it gets really, really nasty, which is why instead of trying to draw this out, we use this picture on the left. The arrows here are how we count up in orbitals. So the first one to get filled is 1s, and then going down 2s, and then 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f. And it goes from there. This is why, although we know that these orbitals, or these sublevels of like 5g and 6g and 7g should exist, before you fill 5g, you have to fill 8s. And 8s would be elements 119 and 120, because we're filling in a somewhat contradictory, somewhat unexpected fashion. By the time you get to 7p, you've actually filled all of the, that's taken all the 118 elements that we've seen so far in human existence. This whole, orbitals fill in a less counterintuitive fashion is actually shown on the periodic table, but I don't know if you've known it yet. You ever wonder why there's a space between hydrogen and helium and why this empty space exists? Well, it turns out that these two columns, there's this tower of 2, and then here there's a tower of 6, and this whole block here is 10, and this is 14, which we've seen those numbers before. If you're filing in electrons one at a time, this here kind of explains. This would be where we're filling 2s, and this would be where we're filling 2p, and this is where we're filling 3s, and this is where we're filling 3p. And we see after 3p is 4s. So not 3d, but 4s. Then 3d. And so these spaces that are in the periodic table allow us to align the sublevels that are being filled by s's, p's, d's, and f's, rather than just going in a straight order. And one final thing I want to mention about the periodic table, because there is always there's this last row before we start, or last column before we start a new row, we can now talk about maybe shortening things up a little bit. Remember that I just said these were p's, 2p, 3p is being filled here. That means that every single of these group 18 elements, these ones in the end, always end in a p6. And from our previous slides, we've seen that after a p is always an s. And so because we know that there's always this p, and then we're always, after that p, we're always starting a new energy level, 2p to 3s, 3p to 4s, 4p to 5s. Sometimes what people do to shorten up their electron configurations is they say go to that end of that row and then we'll start counting from there, which is what I did at the beginning of this video, where I just said let's ignore the first two energy levels. Well, that's kind of what we do. So if we wanted to write the electron configuration of sulfur, we could say 286. We could say 1s2, 2s2, 2p6, 3s2, 3p4. But really, all of this is the same as just whatever neon is. And so as a shortcut, if you're allowed in the problem, if it doesn't say otherwise, you can just say in a square bracket neon plus 3s2, 3p4. And as chemists, we're all going to understand there's more here. We're just not going to show it because that's a lot of numbers. Thanks for watching.